Due to the current plans for the decarbonization of the grid, the energy infrastructure will soon experience major changes and could become more vulnerable to substantial risk of cascading outages with potential blackouts in major cities. So to minimize disruptions, we need to effectively understand, forecast and control the response of complex systems to outside perturbations. So this requires tackling two major technical challenges. One is to devise a robust control algorithm that can suppress abnormal behavior in the systems, and another one is to control local behavior of subsystems when these have a potential to disrupt the whole system. So there are several questions of high importance. One is how we reduce the chance of the lights going out, and another one is, if it will happen, how we prevent the spread of power cuts. My name is Caterina Spătaru and I work at UCL Energy Institute in London, and I spend most of my time developing mathematical and simulation models that help us understand how systems work. So my research is multidisciplinary, and my vision was to bring together experts from different disciplines and challenge our thinking. So I came up with a name: BPAS, Blackouts, Preventions and Solutions through Multidisciplinary Techniques. Collaborating across 4 UCL departments: Energy Institute, Department of Security and Crime Science, Department of Biochemical Engineering, UCL School of Life and Medical Sciences, Cardiology Department, Heart Hospital, the BPAS project intends to initiate academic cooperation in order to understand and develop multidisciplinary techniques for managing the risk of power blackouts in emerging energy grids. BPAS is a project with a topic that connects several domains of research to answer certain questions. So what do cascading failures in power transmission, computing networking, finance, biology, medicine have in common? What do power blackouts and cardio outages have in common? How we can prevent them, and if it happens, how we can prevent the spread of them? Can we, for example, apply methods from medicine, biology, finance to power engineering, or vice versa? All of them are manifestations which can lead to failures, and cascading failures may happen in many types of systems, including power transmission, when one of the elements fails and shifts its load to nearby elements in the system. Medicine, when heart's pumping function is compromised, leading to a cascade of limiting symptoms and poor overall body function. In finance, when the failure of one financial institution causes a domino effect. Biology, when ischemic cascade, in which a small ischemic attack releases toxins which kill off far more cells than the initial damage. Transport, when the failure of one segment has an impact on the traffic within the broader transport network. And computer networks like internet. They all can be very costly, and they typically affect many people. So a failure in a system of interconnected parts can trigger the failure in other parts, and the rapid spread of a cascading failure may finally put the grid at risk and make it collapse. So this is important because mitigation of blackout risk should also account for dynamical effects in complex self-organized critical systems. So for example, some methods of suppressing small blackouts could ultimately increase the risk of larger blackouts. So when something goes wrong, we need to have the ability to decouple networks to prevent the back and forth effects between them.
We look at project planning, really. We're trying to understand how certain actions may relate to the objectives that some organizations, some stakeholders may have. These stakeholders may be the shareholders of a company, or maybe the general public, maybe the government representing the public. And in this case, energy and security, what we have is a system which is composed of two parts, or two systems. A supply system which creates, transmit and deliver energy, to another system which is the demand system, and these two adjust each other based on what they can do in practice. And then we have the rest, which is the environment. So when we have our system and we have our objectives, what we are trying to do, and that's really what we mean by security, is to ensure the manifestation of certain states and certain dynamic for that system. We want to define what is acceptable for the system, the states that we want to see happen, and what's not acceptable. And there may be a cost associated or a value associated with these different intervals. And now we have a complementary goal, which may be of preventing the manifestation of the undesirable or undesired part of those states and dynamics. So being able to understand what the organization wants allow us to define what the system should do and then what we don't want to see happen. Energy security strategy, which was written in 2012, and this is what I got from it. Government is primarily concerned about ensuring that consumers have access to the energy services they need, and they define it as physical security, at prices that avoid excessive volatility. So two components, the cost, financial cost, and access to energy, which is about the service.
Energy security, we can define it as provision of adequate energy services for human well-being that are affordable, reliable and sustainable.
To have security of electricity means to have both security of the sources. We need to have enough energy sources to produce electricity in the long term, and also of course we need to have a reliable infrastructure to distribute energy around. There are different definitions about security. We can speak about adequacy as the ability of the electricity system to supply the aggregate electrical demand and energy requirement of the customer at all time in normal operation or operating conditions. And this is the idea of adequacy. Then we need to introduce the idea of security, that basically is the ability to withstand the perturbation. So we have something happens against the network, a failure, an attack or whatever, and the network is, should be designed and operated in such a way to be able to survive to this abnormal event. And so we can define it as the availability of good reactions to external abnormal perturbation, maybe natural, accidental or malicious, and to keep the system feasible anyway. We can think to reliability as the ability to provide the service, that is, means to supply the loads with high level of probability, and that implies that to be reliable, the system needs to be at the same time secure and adequate. And then we can use the word robustness to qualify high level of reliability of the system, or the other way around, we can speak about vulnerability as a way to quantify the low reliability of the power system.
We can look at a hierarchy of energy services when we're doing security planning. First of all, we have core services, which it's immediately dangerous to interrupt. Water and food supply, domestic space heating and lighting, emergency services, communication systems, hospital systems, etc. Then we have services of intermediate importance, things like provision of social services, production of short-lived essential commodities. Part of security planning is to get a degradation of these energy services to degrade gracefully to the core, and hopefully you'll keep the core services. So here's some examples of energy security in the principal modes of failure of our energy system. These security failures, system failures, have different temporal duration, could be a matter of seconds or minutes. A tree on the line, it might be a matter of hours when you have electricity transmission failure until it's fixed. Some are local, like local transmission failure.
There are different kinds of threats that can harm the power system operation. Generally speaking, a threat is something that is potential, may happen or may not. And so is a potential cause of unwanted event which may result in jeopardizing a system or an organization. Usually it connotes an initial event that can cause harm to the system or induce it to fail. For example, if I have an attack, a terrorist attack is something potential. If I have a terrorist threat is something potential, then I can have actually an attack, so I can destroy an element of the system, let's say a tower, a line, and then it can propagate. So that means that this threat has to be materialized to a certain part of the system to take effect. And basically the implementation of a threat is a disturbance to the operation of the electricity infrastructure. We can, broadly speaking, categorize the threats in terms of natural, accidental, malicious, and we call systemic, that is the emerging threats related to the new ways in which we think and operate the power system. But the idea is how we do vulnerability identification. That has been proposed this idea of complex network applications. Complex network applications are related to the topology of the network. So the idea from a power system perspective is that the power system is like a glass in which we have the glass and we have the level of the water in the glass. One of the reasons why power system guys don't like these topological approaches is because we don't take care of the level of the water. They say, how? I mean, if I have the same failure in a peak hour of off-peak hour, the effect can be hugely different. And I mean, the level of the power over the grid is the level of the water in the glass. So what we do with the topological analysis, we focus on the structural vulnerability, neglecting the operative state. We'll see if we have a hole in the glass, but we don't care about the level of the water in the glass. Of course, if I have the hole here and the water is here, I have no leakage of water, so it's not an issue. Anyway, again, structural vulnerability is a part of the problem, it's not the whole story.
Some examples here which illustrates the diversity of attacks. So we have, for example, in India, we have a Maoist group, also called Naxalite, who destroyed some electricity transformer using explosive, which is called ID here for improvised explosive device. You'll find it later again, resulting in power disruption. In Egypt, you have militants who detonated an ID made of TNT, targeting and damaging a pipeline that supplies gas to Jordan and Israel. So we have a different type of target, but the method here remains the same. In Russia, people targeting a hydroelectric power plant. So again, a different target, but same methodology. In Russia, we have also, again, assailants detonated an ID under a propane tank at a gas station. So obviously here, the idea was to use part of the system to cause an even bigger threat. Philippines, we have, again, IDs placed at the base of 2 electricity transmission towers. And we have a large number of such incidents targeting towers. More recently, in Canada, you have theft of copper wire at a hydro station. You have in the UK last month, and that's just one example out of many, a live cable dug up and cut. And again, the cost of this is tremendous. And then persons broke into 4 substations, metal theft and power loss. And what we found here is that people do not necessarily know what they deal with when they cut those wires. We have extremists who may be involved in targeting the energy infrastructure. And we have metal theft, which may be really a petty theft in a sense that the amount of money that they can gain from that it can be very low. But the consequences in terms of cost to repair the infrastructure are just really disproportionate. The targets, as we've seen, we've got many. Most of the countries, although I haven't done the statistics, but just looking through quickly, seems to be about Pakistan and Colombia, as I said, where you have a number of terrorist groups, a lot more than metal thieves, for example. Then we have various components targeted, so it may be the generator in some cases, it may be the cables, the grounding cables. In terms of impact, there are obviously power loss that may happen, financial cost with repairing, as well as injuries and fatalities. In some cases, the perpetrators are injured. In other cases, they actually target someone at the substation. And then obviously in the case of terrorism, you also have political implications. Would it be possible for an insider to modify the system so to facilitate cascade effect without being detected? And that takes us to scenario inference, where if you have, for example, a number of actions, you know of a number of actions, are you able to infer from that what the plan might be? And you may use the attacker goal as a priori information.
The difference between the definition of blackouts and cascading failures is that blackouts are caused by cascading failures, while cascading failures do not necessarily cause blackouts. So when do blackouts happen? When n-1 contingency analysis has not been done properly, when more than one thing went wrong.
How we prevent blackouts happening? So the power systems have to be robust, and they run generally around the world into n-1 security criterion, because bad things happen. And if they happen, we must not have cascading event like a domino type effect. So how to prevent a cascading event? Power system must be secured not only under normal operating conditions, if everything is fine, but also if one of the elements fails. So it means there must be enough redundancy built up to the system to prevent if you lose a line, a transformer, a generator, whatever. And that's referred to as n-1 criteria, because one element can fail, and the system must have enough inbuilt redundancy to survive it on its own. That means there must be enough generation to cover any generator trip. It has to have also transmission redundancy, and that's why transmission networks are meshed. They have a number of parallel connections, a number of paths to get you from A to B, because if one line trips, the other parallel transmission lines may carry the load, and of course the system must be run enough so those other parallel lines will not be overloaded. In this country, actually it's not n-1, it's called n-d, d for double, because on transmission lines, on transmission towers, we have two transmission lines running in parallel to two different locations depending on configuration. So the idea is if the lightning strikes, for example, it will bring down two lines, so that's why it's called double. Generally speaking, if we're talking about underlying reasons, blackouts happen when more than one element fails.
Here is a list with the major blackouts. One of the major problems was transmission failures, and all had a major impact: energy not supplied, cost of economy, and political fallout. This was one of the most serious blackouts of the last 2 decades in Europe, which affected about 10 million people, alongside the Italian blackout in 2003, which affected more than 50 million people. What happens was a failure, a tripping of many high voltage lines that started in the North Germany. The system average interruption duration index, which mainly represents the sum of customers which sustain outage minute per year divided by the total customer served, and the system average interruption frequency index, which represents the number of customer interruptions divided by the total number of customers served. One problem in reporting this average data for a state or even for a utility is that it does not address either the served area is urban or rural. And for instance, utility may have an average of interruption duration index of 2 and can have a 25% of its customers in an urban area with system average interruption frequency identification of 0.2. So downtown areas tend to be wired with underground spot networks, which are more reliable and costly than radial overhead networks, which can be found in suburban area and rural areas.
The problem was that there were stronger winds on the day than forecasted. We are talking northern Germany, a lot of wind generation. And E.ON, the local German utility, concluded empirically, without doing proper calculations, that the situation would be still n-1 secure. But it wasn't. So what happened? They disconnected the line, high power flows, they tried to do something about it by so-called substation reconfiguration, but again they didn't do it properly and they make the situation worse. Because they made the situation worse, one line tripped, the next one line tripped, and etc., because it wasn't n-1 secure. What was the result of that? Europe separated in 3 different areas, 3 different frequencies. Power was exported from the east to the west, so that means here was surplus of power, it means the frequency went up. Here was deficit of power, so that means the frequency went down to 49 Hz. And the Southeast Europe, it was just slight deficit. The Indian blackout last summer, It was quite amazing. You can again see some pictures, total deadlock of traffic. So if you look at India, it's divided into regions. So western regions, northern regions, eastern regions and northeastern regions. And there's also southern region which is connected by high voltage DC. So on the 30th of July, 36 gigawatt lost. The northern region basically took more power than it was supposed to take. And it caused very high loading on the tie lines. Now the transmission system operator, the Indian transmission system operator, requested the northern utility to reduce the load and the generation in the west to also reduce. But the problem with India is that basically they didn't listen to them, which means they didn't reduce the demand in the western region. Line were overloaded and they tripped. The system was not N-1 secure. There was a tripping to some technical reasons, and that it was followed cascaded tripping. The whole country went black. So fundamental reasons for Indian blackouts, there were some market rules were flawed, but basically they encourage uncoordinated self-dispatch.
There are many consequences. So for example, during the blackout in 1965, doctor used temporary lighting to perform brain surgery at St. Vincent's Hospital in New York City. Another example is during the blackout in New York in 1977, which left about 9 million New Yorkers without power, posed plenty of inherent problems leading to bad behavior. During the blackout in India in 2012, hundreds of trains stalled across the country and traffic lights went out, causing widespread traffic jams in New Delhi. Emergency workers rushed generators to coal mines to rescue the miners trapped underground. And another example is during the blackout in London, the London Fire Brigade took around 400 calls and made 100 rescue of people which were stuck in the lifts. So 60% of the London Underground was affected and 270 sets of traffic lights were hit.
So the question is, in GB, in this part of the world, are we safe from those kind of things? Because we are in splendid isolation. GB, as I said, is connected. Here is the Irish link is missing by those red DC lines with the rest of the Europe, which means we are not affected. And interestingly, when there was this blackout in 2006 in Europe, France was in heavy deficit. They were on the brink of the total blackout. Yet, through the link to Britain, they were still exporting power, which they made it worse. So the first thing they should have done, they should have cut out the power on the DC, but they didn't. DC links are completely controllable. You can do with them whatever you want. The beauty of the British system is that we have one transmission system operator. National Grid runs the whole network, so it means they know they are basically the big brother who is watching us, and basically they do whatever they want to do. No problem with collaboration. It means we are inherently safer than Europe. It costs more, but we are safer than them. That means that there were no wide area blackouts in this country. There were some local ones. I'll talk about a few words about them. But then basically there was never a problem with large area of the country being blacked out. But as I said, there were some local problems.
People tend to learn from the past, and lesson learned from the blackouts contributed to improvement in communication and coordination in Europe, in the United States, and so on. The energy infrastructure will soon experience all these major changes. Will be highly stochastic generation and demand. Two major technical challenges, in my opinion, one is to devise a robust control algorithm that can suppress abnormal behavior in the systems. And the second challenge is to control local behavior of subsystems when these have a potential to disrupt the whole system. Static failure models, which focus on topology vulnerability, but they do not describe the evolving process of cascading failures. And some use realistic power grid networks, some use inappropriate networks topologies. Then are dynamic overload failure models, and they have three components: triggering events, flow redispatch, and additional line trips. They are based on the graphic theory. Then are model based on realistic power flows and stochastic models. Currently, none of the existing tools do properly incorporate into the analysis substation-related outages, remedial action schemes and operating procedures. So most existing tools have limited capabilities to address dynamic system behavior under cascading type of events. So what we need is better real-time tools for operators and reliability coordinators to automatically perform analysis of cascading outages that are transiently limited and enhance existing tools to fully simulate protective relays operation. We need mathematical tools which can model all energy systems from generation, transmission and distribution. So for the past few years I worked together with my colleague Mark developing an all energy system model, a dynamic energy model called Dynamo, researching how renewables and other energy resources can be deployed to meet demands and how demand-supply matching with storage, dispatchable generation and transmission, capturing the behavior of all the main elements of a system.
So we have three services, I call emergency, that's vital services, core services, economic, that's for economic production, and leisure. This is our emergency demands here, our essential core services, then economic, and then we should have the leisure actually, which I'm afraid is invisible. It's actually the difference between this red line generally, there. So that's our total energy demand varying through the days, built up by essential core services, economic and leisure. The blue line here is our primary supply of renewable energy, fluctuating. This is our emergency demands here, our essential core services, then economic, and then we should have the leisure actually, which I'm afraid is invisible. It's actually the difference between this red line generally, there. So that's our total energy demand varying through the days, built up by essential core services, economic and leisure. The blue line here is our primary supply of renewable energy, fluctuating. So you have these primary flows coming into the system here. You've got your demand there, and then it's modified going through the transmission links and storage. Dynamically changing all the time. Your demands are changing all the time, your supplies are changing all the time. So you have a dynamic management problem. And this failure here of service here is when one of the components fails or the storage levels drop to zero. Given the values of these different services, 1,000 pence a kilowatt hour for emergency down to 5 for leisure, and we can put in the costs of our storage and distribution and primary energy supply. We can put in capital costs for those. Then what we can do is we can optimize. So we can have an objective function, which is the total cost of the technologies minus the cost, the value of service that you're provided, and then you can optimize the system and find out, given the valuation you place on energy services, what the optimum configuration of the system is to give you your least total economic cost.
Why do we have a cardiovascular system? We have a cardiovascular system to deliver oxygen and nutrients to the body. And again, I was thinking, is this like an electricity grid? Or is this more like the delivery of coal to local power stations? Because actually the power generation takes place within tissues. And what we're delivering here is the fuel to metabolically active tissue, where they generate energy which is then used for cellular processes. So we have a system that receives blood from the body to the right side of the heart, which then pumps it into the lungs where it's oxygenated. And then you have a left-sided system which receives that blood from the lungs and then pumps it around the body. The heart itself is 2 pumps in series. It provides unilateral and pulsatile flow. But the key thing is that it's adaptive. And it's adaptive at every level. The vessels are adaptive, the heart is adaptive, the cells are adaptive, the metabolism is adaptive. And this is a computer model of the heart, just to show you. It's sort of a bit of cardiology porn, really, but it shows the heart pumping. You're looking at, it's not arranged sort of two top chambers, two bottom chambers. This is the left atrium at the back of the heart, and now you see those two valves that you were talking about, the one on the right, the one on the left, which are there to ensure you have unidirectional flow. The regulation of the heart system is mediated through its electrics, if you like. So it has its own natural metronome, pace setter, pacemaker, which is called the sinoatrial node. And that sets the rate of the heart. But the pump will respond to pressure. So there's a law, which the more you stretch it, the more it contracts. And again, that's determined by changes in flux of calcium within the cell. But in order for this muscle to work, it also needs a fuel supply. And these are the arteries that you've heard about from Ivan. So in that big vessel which comes out the heart, the aorta, there are some further vessels which actually supply the heart muscle itself. These are the coronary arteries. What the heart has to do on a daily basis, it has to beat 100,000 times, and it has to shift 10 tons of blood. That needs a lot of energy. And it can't store that energy. So it's having to make the energy on the fly. One of the ways in which the heart adapts is it can use many different fuels to make that energy. If you've just eaten a meal, you'll have a lot of glucose whizzing around. So it can use that sugar and turn it into energy to make the heart contract. If you haven't eaten for 12 hours, you start to use stored energy stores. So you start to break down fat stores. And you generate what are called free fatty acids. So these can then be used as a fuel. The heart is very promiscuous in the fuel that it uses, but it adapts to the prevailing conditions. That's the problem with the heart. So if you have a power outage, you can call the engineers, but it's usually too late. Why does the heart fail? Well, the heart fails because you may damage the pump mechanism and all the electrics that go with that. So you've already heard about myocardial infarction. You've cut the fuel line. So you're no longer delivering energy to the pump. Now that may result in a catastrophic failure of the pump. But remember that there are two vessels here. There's one on the right, one on the left. The one on the left supplies about 2/3 of the heart. So if you get something which blocks that very proximally, then that usually results in serious consequences. But if it's a little bit further down, or if it's on the right side, you may survive that initial blockage. Unless it triggers an arrhythmia which kills you. So it's just cutting the fuel line, or one of the fuel lines, is not necessarily a catastrophic event. You can essentially damage the wiring, if you like. So you can damage the pacemaker, or you can damage any of the wiring elements downstream. So for example, if you damage this electrical link between top and bottom, you call what we call complete heart block. The top and the bottom can no longer synchronize with one another. You can disrupt this normal, regular activation of the electrical impulse throughout the heart. That's what you were showing. So ventricular fibrillation is when the heart's sitting there doing that. So there's no coordinated electrical activity. How does the heart avoid blackouts? Which it does pretty much all the time. The time when it starts to black out is when it's diseased.
When a patient suffers myocardial infarction, this is where they suffer a blockage in one of the arteries that supplies blood to the heart muscle. Now, heart muscle is metabolically very active. It needs a lot of oxygen in order to efficiently pump. If there is a blockage, the blood cannot efficiently feed the heart muscle beyond the point of the blockage. And so that heart muscle starts to die. It becomes ischemic, which means it's starved of oxygen. And we have what's called an ischemic cascade, which is where the heart muscle cells themselves begin to die, the blood vessel cells begin to die, and the blood vessels begin to regress. When the blockage is eventually overcome, we then have a sudden influx of inflammatory cells. And these inflammatory cells themselves, even though we need them to fight infection and to help to heal and sort of clean up debris in our tissues when we have an injury, actually in the context of sort of heart attacks, they can be very debilitating because they themselves start to damage the heart muscle tissue. And they also produce factors that lead to scar tissue formation. And once scar tissue is formed in the heart, we lose functionality of that part of the heart. A cascade that leads that red area to increase in size. And a very simple analogy that I've seen used before and that I actually quite like is that when a patient suffers a myocardial infarction, it's a little bit like dropping a pebble in a pond. You've got a completely smooth mill pond, you drop a pebble in, and that initial impact is like a myocardial infarction. The next thing that happens is you have a ripple spread from the point at which the pebble hit the water. And I know this is sort of very oversimplifying things, but essentially that ripple is where the damage zone increases in size, and eventually the damage zone will become bigger and bigger and will eventually lead to the patient suffering from heart failure.
As in your house, the heart house also needs plumbing, so this delivers fresh blood from the aorta to supply the walls of the heart with blood. So when the walls contract, they push the blood out to the body, and when the walls relax, they allow the heart to fill with blood again. So these cycles happen about 70 times per minute. So how electrical heart system works? The sinus node generates an electric impulse and sends it through the heart, causing it to beat. And then similar to a light switch in your home, but in this case the sinus node can switch itself on and off automatically. So when the sinus node is turned on, an electric current spreads to activate both right atrium and left atrium, and then the AV node, the atrial ventricle node, so that the AV node works like a delay station. So another example is like an electrical turbine engine. The sinus node generates electric impulses spontaneously all the time, and the rate of its electric impulse discharge is determined by the whole body needs. So normal blood circulation to the brain is like an arrangement in a city. The current, voltage, charge, resistance and capacitance of a circuit correspond to flow, blood pressure, volume, resistance and capacitance of a simulated cardiovascular system. So if an electric fault happens, it will cause all area to collapse. So what are the correlations between the electrical characteristics of a system and their mechanical parts? One is blood vessels resistance, depending on blood viscosity and vessel diameter, is simulated by the resistors, and the blood inertia is considered using inducers. The vessel compliance is simulated by capacitors, and atriums are simulated as part of the venous system without any contractions. Ventricles are simulated as a section of blood vessels in which its resting capacitance can be decreased and then returned to the resting capacitance. So there are similarities at low level as well as at high level, but the most similarities can be defined in networks. The analogy is that power station heart changes electricity, blood output to match demand via the transmission system. Then there is the control of the power station heart itself as station heart demand changes. And for example, for power system, as demand increases, voltage falls and more coal steam produced and put into turbines. So the lower the voltage, the more energy into the power system, which slightly increase the power system. So for heart, the more demand, a hormone change the electrical control of the heart to increase the pulse rate. So the basic control is the same. Then if we add lots of this across a network and with time delays, transmission or node failure, you can get cascade. In mathematics, networks are called graphs. The entities are nodes and the links are edges. So graph theory starts in the 18th century with Leonhard Euler. And since then, the graphs have been studied a lot and to model existing networks. For example, networks of highways, social networks. Now, networks are larger as a result of a technical advancement. For example, web networks are now thousands, millions or billions of nodes, impossible to visualize. Modeling real networks becomes more difficult, And often real-world networks do not live in isolation, but depend on interact with other networks. So coupled network is a system of networks coupled together. For example, the communication network depends on the power grid for power for the switches, while the power grid depends on the communication network for control and data acquisition. We have seen that some approaches applied to financial systems has some similarities to the epidemiological literature on the spread of disease in networks. So we found two key differences. In most epidemiological models, higher connectivity simply creates more channels of contact through which infection could spread, increasing the potential for contagion. In finance, greater connectivity also provides counteracting risk-sharing benefits as exposures are diversified across a wider set of institutions. Another example is the global economic crisis, which is akin to a power blackout. In both cases, a disturbance in one part of the system results in a cascade of failures through an entire network. So in the case of a power blackout, a single down power line causes power to be sent to another part of the grid, which in turn leads to new overloaded and ultimately to a cascade of failures. So there is a need for software algorithms that incorporate the models that are necessary for simulation of the cascading events. One example is the integration of relay models and control device models in the dynamic simulation software tools. So we need optimization and analytical tools that enable to dynamically optimize the performance of a power system. Also, we need methods able to isolate the influence of disturbance in one part of the system to the entire system, and methods to isolate the area where a disturbance occurs. So in order to specify the critical relays that have a high index of vulnerability, a computer-based monitoring and control system can be installed in substations. So we need to develop methods to mitigate emerging blackout risk.